welcome to this lecture on mass transfer. My name is Reinhold Kneer, and this lecture is concerned with phase equilibrium. The phase equilibrium can happen between two liquids or a liquid-gas interface. And here's a little sketch that shows, let me pick the laser pointer, sorry. The sketch shows here liquid oil sitting on liquid water. This is the just the coordinate, the geometrical coordinate, and that's concentration or mass fraction of a certain substance whose course is here shown as well. And the question is, how does this concentration course look like depending on some boundary conditions that we pick? That's what we will also have a look at in this video here. Let's first understand what is phase boundary, phase equilibrium. We know, looking around or in nature, we often see a phase boundary as the surface of a liquid that is sitting in a gaseous environment, being a droplet, a river, or a lake, or whatever, bath tube. So we have a liquid phase and a gas phase, and we can optically easily determine here the phase boundary. And we may have the case that in the liquid phase there's a substance A dissolved, for example, like CO2 or nitrogen. If it's CO2, it could be sparkling water. And the substance A may also be present in the gas phase. So our situation is we have the substance A, which is in the gas and the liquid phase. The system is in equilibrium, and equilibrium here means that the number of molecules leaving the gas phase and entering the liquid phase, and the number of molecules leaving the liquid phase and entering the gas phase is the same. That is the nature of this equilibrium. When we here think back of what we had in heat transfer, then we talked equilibrium at such a boundary with the temperature on the one side of the boundary and the temperature on the other side of the boundary being identical, which is not the case if we look here at mass transfer and look at concentrations. The property which is identical, the thermodynamic property, if we talk substances and movement of substances, would be the chemical potential. That's something that we will get to know not in heat and mass transfer, but later on in a master course that's available in the moment only in German, and that's called Warme- und Stoffübertragung 2. Now let's move on here to understand what is the concentration in the liquid phase and the gas phase, and without going to solve complicated differential equations, is there an approach that is easy to use and ready to use? And the answer is yes, there is, and this approach will be shown in a second. First, I would like to explain why we might have a difference in concentration of substance A in the liquid and the gas phase. How much, if we want to dissolve, for example, CO2, how much we can dissolve depends on the nature of the liquid, the pressure, and in short, that's the intermolecular forces or intermolecular interactions that determine that. Very often, as the molecules in a liquid are much denser packed than the molecules in the gas phase, we have much more pronounced intermolecular forces in the liquid phase than we do have in the gas phase. And the result is that some substances are easy soluble in liquids and others even almost in a vanishing amount. Now, if we want to describe this concentration, we have now a dependence of which substance we talk about, what the temperature is, what the pressure is, and this is quite a number of dependencies that we would like to overcome by using a rough approach, and that rough approach is to use the Henry coefficient. The Henry coefficient is here written with a capital H, and it relates the concentration of a substance here called I, that's our substance A, in the liquid phase and in the gas phase on either side of the interface, with the concentration defined as a number of moles divided by the volume. And if I know the Henry coefficient and I know one concentration, I can calculate the other one. Henry coefficient, as you see by the equations, are non-dimensional property, which may cause some headache, and I will come back to that on the next slide. If you want to understand how much masses or how much mass is going from one side to the other, you have to look at the mass fraction, and we can, as I showed in one of the earlier videos, come from the concentration by writing it as the number of moles over the volume, number of moles then being the component mass divided by the component molar mass, and volume expressed as mass divided by density. We can come up with a relationship where we relate this concentration to mass fraction. And if we look back at what I was shown on the previous page, that was this Henry coefficient, and if we write the concentration on the liquid side here with this red expression according to this, and on the gaseous side by this orange expression, the molar mass cancels out and we receive what is here written on the right hand side. And if we now solve this for the concentration on the liquid side, we get this expression. So we get the mass fraction on the liquid side equals the mass fraction on the gaseous side times the Henry coefficient defined by the concentrations with a superscript Cc times a density ratio. And we can combine that and name this also Henry coefficient. And in order to mark the difference to the previous one, this one has an asterisk. And now you see the Henry coefficient being non-dimensional. If you just pick it up from a table and it's not explained there how it was formed, well, it's difficult to be here and to understand exactly which one to pick. So there should always be an explanation if it's the Cc or if it's built with a density ratio. Now this Henry coefficient, as shown as on the previous one, depends on this density ratio. If we put in values for our case on the left hand side, we have water, density of water roughly 1000 kilograms per cubic meter, air, density of air depending on temperature of course, let's say 1.3 kilograms per cubic meter. So this ratio here is roughly 1 over 1,000. And this means that this gas phase concentration is divided by 1,000 and multiplied by this Henry coefficient. So that's why often we have a much lower concentration in the liquid. But it depends on the value of the Henry coefficient. And this is determined, as I explained, by intermolecular interactions. Now let's look at a steady-state equilibrium case. As we said, we have the substance in the water and in the air. We take the value of the Henry coefficient that gives us, once we know, for example, a surface mass fraction of substance A in the liquid, and can determine the substance in the gas phase. As it's equilibrium, we will have here a constant value along this coordinate. Now if you go to unsteady things, we will see that this jump in concentration that we observe, which is a major difference compared to what we have in heat transfer, this will be kept, but other things change here. So the transient case, for this one I have to take one assumption which is mostly generally valid, and this assumption is that the phase change of a molecule going from either side of the phase boundary happens much faster than other transport processes, for example diffusion in the liquid or diffusion in the gas phase. And this means at the interface the equilibrium values are given by the Henry coefficient, defining this jump here. Now we will sketch a situation where we assume that the substance A goes from the liquid side to the gas side. And in order to have a flow in this direction, we ought to have a course like this. a higher value of mass fraction within the liquid, it goes down towards the surface, we get a flux towards the surface, and although the values here in the gas phase are higher than in the liquid phase, we will have transport of substance A into the gas phase. And in the gas phase then the value also goes down when we go away from that surface. So please note we have the jump, and the transport direction is giving us such a gradient on either side of the interface. And as I just said, this is here again in writing. Now let's move on and look at an example. For example, a droplet with that substance in a gaseous environment. Now we plot. Please note that now the axes are changing. That's now the mass fraction, and that's the coordinate. So we have the center of the droplet and its surface here. And as we had in heat transfer, this is then a point or axis of symmetry. So we have a zero gradient in the center, and we assume that the substance goes out of the droplet. So we have a decrease here in the value of the mass fraction. We have that jump defined by the Henry coefficient, and again a decrease towards further out. So we have the substance A leaving the droplet and entering the gas phase according to these two profiles, and happening although we have a higher value here than we have here. And with that we look now at the equilibrium between two liquids. It will be treated in a very similar way. As I explained in the beginning, we talk here oil sitting on top of a liquid and having again the substance A in. The approach now to describe what happens at the interface is no longer done with the Henry coefficient, but here with this Kn, which is Nernst distribution coefficient. And this one relates the mass fractions in these two liquids at the interface, and it's the mass fraction of that substance that we want to trace here. And in the case that we are showing here, very similar to before where we had liquid and gas phase, if we have a higher value in the water here, we have a transport towards the surface. The Nernst distribution coefficient defines us the two values here, and then we have again a transport into the oil. And this means the mass transfer of substance A takes place from the water towards the oil. So we will work with that in our exercises to give you somehow a feeling for what kind of values are possible for Nernst distribution coefficient or the Henry coefficient. Now with that, I'm coming to some comprehension questions, and one would be, which quantities determine the ratio of the mass concentration at a phase interface between liquid and gas phase? It's clearly explained in the video. Have a look and try to formulate it yourself. And the next point would be, why do the mass concentration at the interface, even in the transient case, correspond to the equilibrium state values? Again, have a look, try to understand and answer these questions yourself. So it has to do with the Henry coefficient here, and have some fun in going more into the details. Thank you for listening.